introduction and motivation section. So here we will be seeing what basically is the GitHub Actions and why we need a scalable system. Yes, firstly, what is GitHub Actions? It is basically a CI/CD automation platform that is provided by the GitHub only. And the major components that make this CI/CD platform are the workflows, jobs, and runners. So workflows are basically an automated YAML processes, or you can say YAML files that we wrote in the GitHub. And these workflow files are designed to trigger based on certain kind of events, like someone committing to a GitHub repo, someone is creating a pull request, or someone is releasing something on that repo. Now, workflow is made up of multiple small units, which we called as jobs. Firstly, why GitHub introduced the concept of jobs. So there can be cases you want to execute some instructions in parallel, you want some execution in sequential manner. So for that, we have the concept of jobs. In that, we can define the proper execution flow, which I'm going to show in the next slide. But before that, the job is basically the set of instructions only, which we will be executing over some machine, and that is basically a runner. In this slide, as you can see, this is basically a workflow. So we used to write these files in the GitHub repos, and these workflows are defined to execute over some actions, like this is designed to execute over a push event. So as you can see, there are 3 jobs like Ubuntu, Windows, and Mac OS, which are running in parallel, followed by some jobs, and then finally the production jobs. So this is basically GitHub Actions only, GitHub integrated CI/CD platform. Yes. Moving on further, why we chose GitHub Actions for Eternal. So first thing is, as it is integrated in CI/CD, as this CI/CD platform is integrated in GitHub only, and we are using GitHub for managing our code. So it will be like easy for all the developers to manage everything in the single place, like writing the code in the repo only, then managing the jobs there only. So they are basically having the complete visibility of the testing workflows, the build workflows, and deploy workflows. They don't have to switch across multiple platforms. And this also creates a confusion for multiple developers because they don't know whether the build was happening, whether deploy was happening, how to debug those things. So everything is going at single place only. Now the next thing is, secondly, GitHub Actions provides us the functionality of self-hosted machines. It means that the jobs that I was talking about in the GitHub section, I can execute those jobs in those machines which are basically present in my cloud only. So it means that it is giving a sense of security and isolation, as everything is running in my cloud only, and I can create any kind of customization over that, whether it's based on the cost or performance, etc. Now, why we need to create this CI/CD platform as a scalable system. So first thing is, there can be 2 approaches. We are running some machines in our infra, and we have hosted those machines on the GitHub for 24/7 time. But the problem with that approach is, there will be very few times when some job is running over those machines, and rest of the time those machines will be idle. So that will lead to a lot of compute wastage. So for that, we have created a dynamic system. It means that whenever some job requests a runner, we just configure that machine, spawn it in our account, and register it to the GitHub. GitHub basically runs the job over that machine, and we just kill that machine after that. So with that dynamic approach, we have achieved around 10x cheaper cost for our orchestrator, which we will going to show in the further slides. Now Nishant will be taking you through the challenge landscape. Basically, he will be showing you some of the challenges which we faced while designing a scalable system.
Now we'll be hello everyone. Sorry for that. Now we'll be reviewing what are the key obstacles and challenges that we faced, which drove us to progress.
Okay, so wait, bro.
And the first major challenge was infrastructure complexity at scale. Given the massive scale that we have 20 plus AWS accounts, multiple GitHub boards, more than 600 plus repositories, we need some standard workloads, we need some standard workflows which can be defined at one place and can be reused by these repositories. Now this comes with another challenge.
Sorry. Yeah. 2 minutes. You can have it in your pocket. Yeah, go ahead.
As we all know that different repos built on different programming languages, right? Some are built on Java, some are built on Python, some are on Golang, etc. So we need our system to be smart enough to filter out what type of job it need to run on for that particular repo. For example, if the repo have the majority of the code in Golang, then it should only run the CI operation related to Golang, etc. And the third one is, now that we have multiple businesses onboarded and or each business have their own GitHub organization, their own AWS accounts, we need a system which can handle the multi-tenancy request. That is, if a request came from a, let's say, Zomato GitHub org account, then it should spawn the runner in Zomato AWS account. Another challenge was the cost challenge, which is our favorite challenge in SRE. So in AWS universe, we have basically two types of instances. One is spot instance and one is OD instance. What are the difference between them? The spot instances are those instances which AWS can reclaim at any moment. And following the same terminology, we are saying that spot runners are those which are spawned on spot instance, and OD runners are those which are spawned on demand instance. Another big difference between spot and OD instances are the spot instances are way much cheaper, providing us 70% more cost opti as compared to on-demand instances. And most of our CI workflows are those which are doing some basic operations like making some calls, doing validation, etc. So we need a system which can provide us both the facility of both spot runners and on-demand runners. Third challenge was the reliability and resilience. So let's say there was a GitHub outage or there was a GitHub API throttling, there was some anomaly, and we want that our system behaves in a well-profiled manner. So we need that our system is more reliable, can handle the GitHub API throttling events, GitHub outages, and can handle the spot interruption as well, now that we are using the spot runners. Fourth challenge was the performance bottleneck. Now, as we all know, now that we have build jobs and what all build jobs basically do, they download all the build dependency again and again and again. And what's the standard solution for that? We introduce the cache, right? We introduce the cache, and over that cache, we download the build dependency so that build time can be reduced. Now that all our CD are on GitHub Action, we need a system which can provide us the cache ability as well. And the last and not least, which is most important one, security. Now, personally, I don't want whatever jobs I am doing, whatever execution I'm doing, no other jobs can access my data, my tokens, it's anything. So I want that my system should be more secured and isolated in nature. Considering these challenges, key obstacles, this is how we orchestrated our system. Now Akshat is going to take you what our orchestrator look like.
After checking out what exactly GitHub Actions is and what all challenges we are having while designing that scalable system.
Sorry for that. Just need it for us. You can keep it.
Let's take a look in the design secrets behind our CI/CD orchestrator. We will be taking you to a high-level overview, like someone committing to a GitHub repo and how it leads to the starts of workflow execution, how jobs are spawned, how that jobs placed over our VPC machines, and how those machines are registered over GitHub, and how GitHub run those jobs over those self-hosted runners. So firstly, assume that there's some users which are committing to a GitHub repo. And after committing to a GitHub repo, let's just assume there is a workflow present in that repo, which is designed to be triggered based on this action. Now, once that workflow is triggered, as discussed earlier, workflow is a combination jobs. It means that now all the jobs will come in the waiting state. It means that they are waiting for some machine over the GitHub cloud to execute its instructions. All those jobs are basically, that loading sign is symbolizing that all those jobs are waiting for the runners in that cloud to execute their instructions. Now, meanwhile, GitHub also generates some events. So some workflow events, basically it's telling us what all jobs are getting executed that moment. And we push those events to our orchestrator, which is running in our cloud. So how we push those events from GitHub cloud to our own cloud, it is basically by a webhook. So webhook you can think of as a simple API service, which works whenever some GitHub event is triggered. So GitHub, so users committed over the repo, workflow starts its execution, job waiting for the runners. Meanwhile, events are pushed to the orchestrator. Now, what exactly orchestrator is doing with that payload, we will be covering that later, but currently, let's just assume that orchestrator is just a black box, picks that job payload, configure a self-hosted machine, and spawn it in the correct AWS account. Now, under Eternal, we have multiple businesses. Currently, let's taking an example of two businesses, Zomato and District. Each business has different AWS accounts separated by environments. So Zomato development accounts, production accounts, same for District also. So Orchestrator will decide in which account it should spawn that self-hosted machine. Assuming that Orchestrator spawns the machine in the Zomato development account. Now inside that Zomato development account, we have two pool of runners. One of our challenge was to run the runners over the mixed pool of instances, like over the Spot also and over the OD also. So it means that we are maintaining the two pools in that AWS account. So once that Orchestrator picks that job payload, it chooses the correct AWS account and choose the correct category and just spawn the runner over that pool. Now once that runner is spawned, it means that we have make a run API call to spawn a machine in the correct pool and in the correct AWS account. Now that runner starts to execute. Now once the runner starts to execute, it basically registers itself to the GitHub cloud. So GitHub gives us some APIs via which we can register our hosted machines to the GitHub cloud. It means that it's just giving a visibility to the GitHub that he can run the jobs over those machines. So now GitHub will run some label matching algorithms and run all those jobs over the self-hosted machines. Basically, this is the high-level system overview only. Now let's deep dive in what is inside the orchestration engine. So what exactly it is doing with that job payload and how it is deciding what configuration should a runner will be and in which AWS account it should spawn that runner. Firstly, with that payload, we run some types of validation checks so that we can ensure we are not spawning runner for the invalid jobs. Because if we spawn runners for an invalid jobs, it just leads to the compute and memory wastage and leads to higher costs for our account. Firstly, we just check if that GitHub job is authorized for the correct AWS account or not. It means that like for different businesses, we have different GitHub organizations. Correspondingly, we have different AWS accounts. So we just need to ensure correct business is requesting runner for the correct AWS account or not. So if that authorization is passes, that job is passed to the second step, in which we just allocate a GitHub token to that job. Now, why there is a need for allocating a GitHub token? There are a lot of actions which we need to do in that job, registering that job over basically registering that runner over the GitHub cloud. And secondly, some other actions which we need to do inside that job only. Now, lastly is the confirmation of a job status. It means that you can think of a scenario like someone created a pull request over a GitHub. It leads to trigger of a workflow. It means that the jobs of those workflows are come in the progress state. They requested a runner, but when we just check the job status, like in the meanwhile situation, some user has closed that pull request or canceled that workflow. So for those cases, we don't need to spawn a runner because else it will only be in idle state at the GitHub cloud and just waste the compute cloud. So at this step, we are just confirming the job status, whether that job is still requesting for the runner or not. And now once those validation checks have passed, now it's time to configure the machine and spawn it in the correct AWS account. So in our terms, runner is basically an ECS task. You can compare it similarly to the Kubernetes pods. You can see the view of, first you can see the view of a job inside a workflow. So inside that workflow, the job has a labels, as you can see after the runs on. Those labels are basically self-hosted account, environment, Spot, OD architecture. So once that job comes in the progress state on the GitHub cloud, we receive these labels. And based on these labels, we configure the machine and spawn it in the correct AWS account. Configuration and account are decided by these labels only. As you can see, we have the account label, so it decides this job is requesting for which AWS account. Similarly, environment, Spot, CPU, and architecture. So choosing the correct configuration, and we just spawn the runner in our cloud. Now, once the machine, or we can say ECS task, has been spawned in the cloud, now look at the picture of what exactly happens when that ECS task, or we can say our runner, starts its execution. So this is basically the inside the runner, like architecture and customizations. So what runner is? Runner is basically an ECS task in our terms. Once that ECS task starts its execution, it does some kind of actions. So GitHub has an open source code named actions runner. So this is a GitHub defined action, which helps us to basically add our self-hosted machine to the GitHub cloud. And some other API calls are also there in that open source code. So our ECS task is basically baked over that open source code only. Once that runner comes up, it registers itself to the GitHub cloud, so that GitHub has the visibility, like these are self-hosted machines which are running in some cloud, and I can run our jobs over that machine. Other than that, in this self-hosted machines, we also have a lot of metrics which we continuously monitor, like tracking how much time a job is running over that runner, how much time that runner was idle, and maintaining the runner status in some other databases also, etc., etc. Lastly, this runner is an ephemeral runner. It means that once we created a runner, registered it to the GitHub cloud, once a GitHub executed a job over that runner, we just kill that runner. We don't want to run another job over that same runner, because there can be cases like the previous job has left some kind of credentials or some kind of PII information in the logs which the second job can access, and it will lead to a security breach. So this was the complete job flow inside the orchestrator, like what all actions the orchestrator is taking for that job payload. There are also some other flows which we are running in our orchestrator to maintain the reliability and performance of systems. Firstly is the spot termination flow. So as we said multiple times, there are a lot of jobs which we are running over the spot machines. It means that we need some kind of reliability in terms of what happens when a spot instance termination happens. Like we have 4 runners, we have 4 ECS tasks running over a spot EC2 instance, and that spot EC2 instance terminates. So what exactly is the behavior at that moment over the GitHub end and over our system? So firstly, whenever a spot machine terminates, at the GitHub end, job continuously try to make a connection with that runner. As that runner is in our cloud, so GitHub tries to make that connection continuously for some minutes. Sometimes this time goes up to 10 minutes and 20 minutes. So at that time, there is a very bad developer experience in terms of UX. Developers will see a type of a confusing screen, no logs coming. So it will be a frustrating developer experience. So to fix that thing, we have created a spot terminations flow. Firstly, the orchestrator as usual spawning a runner over the EC2 machines. Now once that runner starts its execution, it basically maintains its status in some kind of database. For our use case, we just chose Redis. And in parallel, we are also listening for the spot events. Like we have the knowledge of which machine is going to terminate in the next 2 minutes. So if we'll receive a spot event, like assuming this EC2 machine in the large box is going to terminate in the next 2 minutes, we just check all the job statuses over that machine. And if some job is still in the running state, we just cancel that workflow and retry it immediately. So in this way, that 10 minutes frustrating developer experience over the UX will be saved. And obviously the users won't have to retry it manually after that 10-20 minutes. Next system that we are running in our orchestrator is the reliable failure handling and retries. So let's say we are saying we are getting a job payload and we are spawning a runner in the correct AWS account. But how we are sure whether that job has got the runner or not? There can be scenarios we have spawned a machine in the correct AWS account, but it got failed while registering to the GitHub cloud, or there are issues happening at the GitHub end and GitHub failed in placing the jobs over those runners. So to make our system reliable over such failures, whenever we spawn a runner for a specific job, we don't delete that payload. After a fixed interval, we just again retry for that payload, whether the job has placed or not. If the job has come into the running state, we just delete that payload, else we again retry and spawn a replacement runner for that. We does the same thing for a fixed number of retries. Even if the runner job didn't get placed over some machine, we just push that payload over some DLQ and have alerts set up over that thing so that we can further debug. There is something mishappening is there either in our systems or either on the GitHub end. 5 minutes over. Last is the GitHub API rate management. So for single GitHub organizations, we are managing multiple tokens depending on the permissions. And so basically in this flow, we are just ensuring each token is getting consumed in the equal amount. So for that, we are running some flows, maintaining the rate limits for all the tokens and choosing the appropriate token for a particular job. And now Nishant will tell you about some of the optimization and performance enhancements. Last year was
Now the favorite part of section. What are the core of that we want to achieve using this system? And what are the other performance enhancements that we did? Because of time constraint, let's see the most important one is how we were able to achieve the maximum saving. Well, there were two actions, there were two things that we did because of which we were able to achieve maximum OT. First is using the self-hosted runner instead of GitHub hosted runner, and the second one is using the sport runners. Now that we have sport runners functionality, our system is more reliable, and the sport interruptions, we found that most of our jobs, almost 86% of our jobs can be run sport runners. So if we see the cost analysis that we fetched from Orchestrator, So let's say if we are using only the GitHub hosted runner, the cost that we will be getting was $0.064 per minute. But on the right hand side, if you see, if we are using the self-hosted runner and 6 is to 1 spot versus oil comparison, the blended cost is $0.00627 per minute, which is given us directly 10.2 times cheaper as compared to the GitHub runners. Another topic that we did was introducing the right sizing. As the Akshat mentioned, we continuously monitor our jobs and monitor the resources and then configure what are the resources that the particular job is required and then use that particular and then define the awareness in such a way that that the job only utilize that resources. Another thing is auto scaling. So instead of spawning an EC2 instances and running the Docker container there, why did we choose the ECS? Was because of reasons. First is using the ECS task API, we were able to utilize the auto scaling functionality provided by the AWS. And the second one was bill packing strategy. What is bill packing strategy? AWS follows this strategy to place as much task as possible in an efficient manner on an EC2 machine. So instead of spawning a new EC2 machine for every new task, it tries to optimize them. Fourth one is we have a code as well, which basically just do the GitHub API operation, list all the runners, and then check if there are any idle runner in the state. If there is a lot of idle runner which are in idle state for a longer duration, then it just clean them. And the last one is using the build caching. So now that our whole CG operations are on GitHub action, we use AWS FSX as our file system, centralized and shared system to cache our build dependency. Why we are using it and FFX? So basically we did some benchmarking and found that using the FSX give us 50% time improvements as compared to other NFS system. And since we need a shareable and centralized file system, we were not able to utilize the EBS. And the last one is monitoring and observability. So now that for monitoring and observability, we are just like the resources within the CAD advisor, making the GitHub API to monitor what are the rate limit left or how many errors are there in the pool. And as the Akshat mentioned, since we have a custom wrapper, we also monitor the journey of a whole GitHub action as well. Here are some of the matrices. It's too small, but so it just shows what are the general matrices that we observe. And the last thing is what's in our bucket list. So first thing is to integrate the Graviton instances as well. Since the Graviton instances are 20% more cheaper as compared to the normal instances, it gives us more juice, giving us more cost of peak. Second is implementing the predictive scaling so that the provisioning time can be reduced. And the third one is using the local layer caching.
So guys, this is all from our side. And before moving to any questions, I just like to mention that we are actively hiring for SRE team at Zomato and for also the other roles. So you can just scan the QR or can connect with us after the event. Let's start with the questions.
Can you throw some light on the engineering cost behind developing this orchestrator?
Engineering cost, this is not the...
That's engineering cost.
Like it was around 2 to 3 months of our project. It will be difficult to exactly calculate the engineering cost, but it was just a one-time effort. Like we don't need to maintain it continuously.
So on what basis do we choose the tools actually? Because I was working with GitLab earlier. So even GitLab we have runners. So they have self-hosted runners and we have public runners also. So now when we work across multiple projects, so one customer wants to have the GitHub and one customer wants to use Azure DevOps. Even in Azure DevOps we have the agent running, and on top of that our demand it just spins up and goes off. So on what basis do we choose the tools or things to orchestrate?
So most of the time we use reusable workflows, and we tell the developer to use the reusable workflows. Now most of our workflows are simple CI operations, simple validations, linters, check, etc. Let's say API operation and all. So for that, we decided to use the spot runner. And let's say if there was a critical migration for them, we prefer them to use the OD runners.
But on the token case, if you want to renew it, so the token expires all of a sudden. So when you figure a pipeline, after 3 months, 6 months down the line, it expires. So you want to renew it. So that node will be automated or just...
You are talking for the GitHub? So GitHub token is basically we are using two types of things. One is the GitHub apps and the GitHub bots. So GitHub apps gives us the token for 1 hour only. So we used to continuously retry it after let's say 20 seconds, continuously generating the new kind of token. And for the GitHub box, we used to have separate user tokens which have the never expiries systems.
So you mentioned ECS, right? Is it ECS on target or ECS on EC2?
ECS.
So when you use ECS on EC2, right? When you install the GitHub runner or the action, it needs to be registered with the GitHub cloud, which you mentioned. And when you do that, how is the networking security enabled? So the GitHub is a public SaaS model, and what you have here plus is your own.
So like whenever we are making that GitHub register runner API call, so firstly, we have whitelisted the NAT IPs of our VPCs over the GitHub. So this is where we are verifying that only the runners from this cloud only can be whitelisted. Plus, we also generate a custom random token via some admin APIs, which ensures that there's overall network has been, the call has been encrypted, like while making that register call over the cloud.
So you have your NAT gateways, which is already whitelisted.
Yes.
You showed the cost comparison for 10x, right? But what was the actual cost when you are running 1 million jobs with GitHub hosted?
After all the optimizations we had done, it was around 20 to like, we can't exactly share the numbers for our organizations, but
Right. So like we use this, like all the official data, and then on the basis of that. So like the optimization was throughout the times. So we're not able to tell you the exact figure, but based on the like official documents, so we compare the cost, and that's how we're able to find out that we have now the tenants.
Okay, so this orchestrator decision was driven by that cost, right? So that cost was
Huh.
huge
yes.
that you have to.
We have taken the example of a single machine and then we calculated the per CPU cost per minute.
Right. So here we, if you see here, we compare the cost for a standard 16 core Linux system, and from the GitHub official doc, we found that this was the cost, and our planning cost was this. So for a single instance, we compared the cost, and that's how we were able to achieve this number.